here's that first sentence. Fast Reed-Solomon code, interactive Oracle proof of proximity. I'm not going to talk about this definition, but I figured I would include it for those who are interested. This is a formal definition of what a Reed-Solomon code is. It's, again, drawn from that same course on algebraic coding theory, which I highly recommend. For the sake of making this like a reasonably accessible to everyone discussion, I'm going to avoid like Reed-Solomon. Discussing Reed-Solomon codes involves finite fields and polynomials in a way that I think we need to do a sort of primer on polynomials and finite fields before I want to have a study club that goes into the details of Reed-Solomon codes. In a very loose way, Reed-Solomon codes are codes that are based on low-degree polynomials. So what do we mean by this low-degree test? It elaborates. It says, FRI is a low-degree test for functions on an FFT domain, i.e. a smooth multiplicative subgroup D of finite field F. This is sentence 1. Again, if you don't have a degree in math, reading this is probably pretty tricky, but maybe it's easier if I take away some of the harder words. What FRI does, given a function called f, FRI proves that f corresponds to a polynomial of low degree. And this word corresponds means is close to rather than is exactly the same as. Bringing in a little bit more language, we have, it's not just low degree, it's low degree with respect to the size of D. And there's this function notation that you may or may not be familiar with. So what's the function notation? What's D and what's F? This notation says that we're associating each element of D with an element of F. So D is a set, F is a set. Given any point in D, we can evaluate the function F with that point as an input. And the output, when we evaluate it, will be an element of F. D is our initial commitment domain. This is the size of our Merkle tree. We construct one Merkle leaf for each element of D. And F is where we do our arithmetic. So it was Baby Bear, it's going to be Goldilocks. I guess it's going to be field agnostic. Adding in a little bit more of that language. Now this is actually the beginning of the paper. An FFT domain, again, not going to get into this too much, but it's a domain where you can do finite Fourier transforms. More or less, it means you can split it into smaller pieces over and over and over again. And not going to get into the definitions of those terms.